So there's the Taylor polynomials for this function are actually this, this, and this up to third order. And again, I've graphed the function has a vertical asymptote here, right? So the function jumps like that. But you can see that here's the tangent line at 1. Then the best quadratic is the green. It actually opens down this time because the function is concave down there. And then the best cubic approximation to the function at -1 is right there. So I hope I'm convincing you with these pictures that these Taylor polynomials really do match a given function if we're willing to take enough of them, right? But what do I mean by match the function? How do we make that precise? All right, that's what we're getting towards. By the way, same function, different center. These are the Taylor polynomials for the same function as that, but instead of centering at 1, I center at 3, right? And centered at 3, these are the Taylor polynomials centered at 3. So if I said find the Taylor series for a function, I give you the function, I say find the Taylor series for it, you should be like, what do you mean? Because asking what the Taylor series is ill-defined until I tell you the center point. So this is these are pictures of Taylor polynomials centered at 3. Up above was the Taylor polynomial centered at 1, and those are not the same. At 3, they're representing the function to the right of the vertical asymptote. At 1, they're representing the function to the left of the vertical asymptote, right? And again, we see the pattern as we go higher and higher Taylor order polynomials. They're closer and closer to the function for longer and longer. Sine of x. Well, sine of x is actually pretty easy to calculate the Taylor polynomial for because derivatives of sine just go cosine or sine plus or minus, right? And, well, here they are. The first and the third and the fifth Taylor polynomial for sine. Sine is an odd function. Odd, 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 right? Each Taylor polynomial is odd because sine is an odd function. The Taylor series, which is generated for sine, is also odd. Not surprising. What I think is surprising is that you can model sine using polynomials like that. I mean, that's just nuts. So what you're looking at here is the red dotted line, again, is the sine. As you can see, this is sine of theta equals to theta. That approximation we use in physics all the time, right? The small angle approximation for sine. But if you were willing to keep, let's see here, I think the purple graph, this one, it's pretty close to sine all the way out to like here and there, right? If you say sine of theta is equal to theta minus 1/6 theta cubed plus 1 over 120 theta to the fifth, that's a pretty good approximation for sine from here to here, right? To plus or minus 90 degrees, right? If you keep and then I guess this must be like the 7th order one or something, right? I think you have to go to like the 11th order to get a full cycle, approximately speaking. You can also play this game to approximate this idea of approximating expressions with Taylor series has applications to physics, but we don't have enough time left to talk about that today. I'm going to skip past that, come back to it later. So, finally, this is Taylor's theorem. Taylor's theorem, it gives us a way of pinning down, possibly, how close our Taylor series is to a given function, right? Suppose you're given a function, you don't know for sure that it's analytic, right? Then to prove that the function is analytic, you need to somehow show that the function matches its Taylor series. You need to show that the thing I've covered up with the whiteboard doesn't happen. All right? In principle, that's what you need to show. And this theorem gives you the tool to do it. It says that if we have a function with k derivatives on a closed interval, this just means that the interval is either a to b or b to a. Okay? So don't sweat it. Then there exists some c inside the interval from a to b, such that the k plus 1th derivative evaluated at c divided by k plus 1 factorial times b minus a to the k plus 1 is equal to this remainder term evaluated at b. Yep.
What do you mean by saying it's analytic?
Analytic means that the function is equal to the Taylor series, which is generated by the function at that near that point in question. This is what analytic means. So the thing I've covered up was not analytic at 0, because the Taylor series generated by the function was 0, and yet the function was non-zero. The good news is sine, cosine, exponential, pretty much everything we're going to look at is analytic. So it's a somewhat academic discussion. Although, you know, this turn of phrase is somewhat academic discussion. Isn't that offensive as university students? Why should academic be a pejorative? Like, this shouldn't be an insult. If you believe in education, why should academic be? I don't know. I'm just saying. So here it is. We're looking, so this is the kth Taylor polynomial centered at A, evaluated at B. That's what this is. And then I'm defining M to be whatever you need to put over here. M times B minus A to the K over K factorial. This defines M, all right? That defines M. You take that, you take A and replace it with a variable T. As I mentioned here, I found this in Real Variables with Basic Metric Space Topology by Robert B. Ashe, which is a lovely little analysis book. It's available in Dover. It's not much. So I take this and I create G of T. This would be the analog of H of T in the mean value theorem proof. Notice that it's anyway. So I take that, replacing the A with a T, and then you notice that if you plug in B, what do you get? Try putting B into this expression. What happens? 0, right? 0, 0, f of B minus f of B, 0, right? What happens when you plug in A into this formula? It's a little bit more complicated, but if you plug in A, it's also equal to 0 because of how M is defined implicitly by this equation up here. So if we have that minus f of B, that's if we subtract f of B from both sides here, that gives us all of this is equal to 0. But that is exactly G of A. So G of A is 0. G of B is 0. G is built from a sum of continuous and differentiable things. So it is both continuous and differentiable. It has satisfied the terms and conditions for Rolle's theorem. Which means what? That means that there exists a C such that G prime of C is equal to 0. All right? So then you just have to differentiate G, which looks like this. After some algebra, G prime of T can be shown to be this times that. But the thing is, this is non-zero when you look at it, and that forces this to be 0. This being 0 at some C is tantamount to saying that there is a point C such that the kth derivative evaluated at C is equal to M, which is what we were trying to prove. And that's Taylor's theorem. Let me put it, so in the same, this is how we actually use Taylor's theorem, all right? Here's what it says. It says that if you can find a bound for the k plus 1th derivative, if I can be certain that the k plus 1th derivative of f is smaller than some number in absolute value, all right, the absolute value of the derivative is smaller than that, then that implies that the remainder, all right, this is the error in the Taylor series at x. This is how far the Taylor series is diverging. Well, it's not diverging, it's a different word. It's how far the series, the Taylor series differs in some sense from the, if I take the function minus the kth Taylor polynomial, right? We'd like that to go to 0. if the function is matching the Taylor series, right? As we take the number of terms in the Taylor series to go to infinity, we'd like that to match the function, right? That is equivalent to saying that the kth remainder term of the Taylor series goes to 0. So an alternative definition for analytic would be that the remainder of the kth Taylor polynomial goes to 0 as k goes to infinity. All right? Now, so this shows me that the f of x is equal to the, the kth Taylor polynomial centered A plus this remainder term. So this is the fudge factor. This is how far, the size of this is how far you are away from the truth, how close your approximation is to the function. Now, I actually have taken the time to make some graphs of this for specific functions, all right? Well, actually, this is worth mentioning. Here's what the theorem says if we just apply it to the case that we're approximating by a quadratic. It says that the difference between the function and the best quadratic approximation at a critical point, which is where we do the second derivative test, right? It's less than or equal to this, which is that. So I'm discussing why the second derivative test is true in light of this. It makes a lot of sense. Just read the paragraph if you don't mind. I mean, I'm out of time here, so I need to go on. But so here's a kind of weird example. I take this fifth order polynomial, and what I do is I approximate it by the quadratic Taylor polynomial at 2. Not at 2, centered at 0. It's the second Taylor polynomial. I'm an idiot. Anyway, so to find the error in T2, I need to bound the third derivative. And so I give arguments here showing that the third derivative is bounded by 92.4 if we're looking at between plus or minus 0.1 of 0. And, that's a pain to actually go through those details, but here's a picture of it. This is a zoom in to 0. This is between plus or minus 0.1. This gray, this is the size, the maximum size of the remainder for the second Taylor polynomial. And here's an actual picture. The graph of the function is red. The graph of the second Taylor polynomial is green. As you can see, we're well within my claimed tolerance. Here's a bigger picture. Zoom out. Zoom out. We're approximating a fifth order polynomial using a quadratic. It's really only matching up to the red term close to here. If you get further away, then that remainder term is no longer bounded like I zoomed in. And I have a few more pictures of this. Here's I actually have calculated the size of the remainder and plotted it, overlaid it over the Taylor polynomial, which is representing the function, and the function itself. And so, maybe we'll spend a few more minutes look at these pictures tomorrow, but listen, I don't actually make you guys do this stuff because this is really above the level of the course, but for understanding of what we're doing, it's important to have this discussion, all right? We will get back to the calculations starting tomorrow again, okay? So, thanks, guys. Let me get the